Welcome to this video on the need for design of experiments, or DOE. DOE is a systematic method to determine the relationship between factors affecting a process and the output of that process. An experiment involves systematic testing to verify a hypothesis. We make purposeful changes to input variables to observe their effects. The core goal is to observe and identify the reasons for changes in the output response. The goals of experimentation include understanding causality, optimizing performance to improve yield or quality, increasing cost efficiency by reducing variability, and accelerating time to market for new products. When discussing inputs, we define factors as the independent variables you manipulate, like temperature. Levels are the specific settings of a factor, such as 300, 350, or 400 degrees Celsius. Runs are single tests executing a specific combination of factor levels. Outputs are described by the response, the dependent variable you measure, like yield or strength. Noise factors are the uncontrollable variables that affect the response, such as ambient humidity or raw material batches. The old way of experimentation is trial and error, which relies on guesswork. While it's fast for simple problems and requires no formal planning, it is highly inefficient and relies purely on luck. Critically, it doesn't explain why a successful outcome occurred. Another older approach is one factor at a time, or OFAT. This traditional method focuses on isolating single variables by holding all others constant and changing only one variable per test. This is often taught in early science education. Using a baking analogy, OFAT involves setting a baseline, then testing different temperatures. Once the best temperature is found, say 350 degrees, you lock it in and then iterate by testing different baking times. The fatal flaw of OFAT is that it assumes independence. OFAT assumes the best temperature is the same regardless of the baking time. In reality, variables affect each other. This is called an interaction. For example, a higher temperature might require a shorter baking time. An interaction occurs when the effect of one variable depends on the level of another variable. A practical example is how the effect of sugar on a drink's taste depends heavily on the amount of lemon juice present. OFAT is mathematically blind to interactions. Since it only changes one variable at a time, it cannot detect how variables behave in combination. This failure to account for interactions leads to suboptimal processes, missing critical performance peaks in complex systems. The solution is design of experiments, a systematic, mathematical method for planning and conducting tests. DOE replaces OFAT by changing multiple variables simultaneously within a carefully orchestrated matrix to capture full system dynamics. The core need for DOE is to discover interactions. DOE tests combinations of factors simultaneously to uncover hidden relationships. It provides mathematical separation, isolating main effects from interaction effects, which gives engineers an accurate picture of total system dynamics. The second core need is to maximize efficiency, which reduces costs and accelerates time to market. DOE uses statistical extraction to get the maximum amount of statistical information from the minimum number of runs, saving time and resources. Consider testing 5 critical process factors. The OFAT approach requires over 20 disjointed runs and completely misses interactions. Fractional factorial DOE achieves results in just 8 to 16 structured runs, while comprehensively identifying both main effects and crucial interactions. The third core need for DOE is to optimize the process. We don't just want a product that works, we want the best possible product. DOE builds a mathematical equation that enables the precise identification of the optimal configuration. The DOE equation allows engineers to create topographical maps, also known as contour plots, which help visualize the ideal settings. By navigating these plots, you can identify peaks for the highest yield and pinpoint the exact ideal settings without guessing. Core need number 4 is to improve robustness. Robustness means a product performs well even when conditions aren't perfect. This ensures consistency under pressure, such as a phone battery lasting long in both freezing cold and extreme heat. DOE helps reduce variability by identifying which variables cause the most variation in the response. This allows us to control the critical few variables and make processes immune to external noise factors, driving higher consistency and reliability in every output. To summarize, the OFAT approach is like exploring a dark room with a tiny flashlight. You only see one path and miss the big picture. The DOE approach is like turning on the overhead lights, allowing you to see the entire landscape and how everything connects. The conclusion is simple: stop guessing and stop changing one thing at a time. Instead, use design of experiments. DOE will save you time and money, uncover hidden interactions, and help you find the true optimal performance of your systems. If you enjoyed this content, please like and subscribe to help others find our videos. Turn on notifications for weekly updates and join our growing community of professionals.